Hello, everyone, and welcome to this episode. Today, we're looking at some multiple choice questions that involve molarity and concentration. So, if you need a quick brush up on molarity and concentration, you may go out and check out some of my other videos. Here, we're just going to be focusing on problem solving. There will be a couple of pause the video moments for you to try some on your own, and hopefully, you'll find it helpful. So, let's get into it. Our first question is a fairly typical type of question. It asks approximately what mass of copper sulfate hydrate, 250 grams per mole, that's rounded, is required to prepare 250 milliliters of a zero point 0.1 molar copper 2 sulfate solution, and then they give you four choices. Okay, so if you're already familiar with molarity, you know that molarity is the number of moles of solute per liter of solution. And that's kind of like a proportion. You may not have a whole liter of solution. You might have a small amount of solution, something like this. But if you had an entire liter at that concentration, how many moles would it contain? And the flip side of that is if you want to know how much is going to be in there, then you can rearrange that equation. Volume times molarity equals moles. Okay? And that's a quick little multiplication that gets you to moles, which we're going to have to change into grams. So something like this, we're going to do 0.25 liters. This again has to be in liters because molarity is in moles per liter. And so that gets me 0.025 moles of copper sulfate. That's what I need. Okay? And they try to keep the numbers simple for us. So 0.025 moles of copper sulfate times the 250 grams per mole. And what that gets me is something very close to 6.25 grams of copper sulfate. And they say approximately, and the closest answer to that is letter B on that example. So, all right, hopefully you found that helpful. All right, and let's do a quick pause the video moment right off the bat. A 360 milligram sample of aspirin, which is a molar mass of 180, is dissolved in enough water to produce 200 milliliters of solution. What's the molarity of aspirin in a 50 milliliter solution? Pause the video, see if you can get this one, and I'll see you back here in a couple seconds. All right, we're going to keep it short and sweet in terms of showing the calculations. You should always show your calculations to some degree. And here we go. So first of all, you had to watch out for the milligrams. This should be in grams because the molar mass is in grams. So 0.360 grams divided by 180. That's a very small number of moles, 0.02. And then 0.002 moles divided by 0.2 liters gives me 0.01 moles per liter, and that is choice C. So if you pick choice C, then great. All right, I'm here to provide a public service announcement for the next one. Here, this whole thing here is for the one question. They give us a huge description of the experiment. They give us some data, looks like a Beer's law graph, and so on. And then the question that's actually being asked here today is the concentration of chloride ions in solution 2 was. All right, and if you go back to solution 2, let's put that over here. Solution 2 had a nickel concentration of 0.04 moles per liter, and that had an absorbance of this. So to be honest, most of this stuff has nothing to do with this question. Sometimes you're going to get questions with lots and lots of fillers, lots and lots of distractors. But if we go back to the chemical formula, for every one nickel, there's two chlorines. Okay? So the concentration of chlorine should be double whatever the concentration of nickel is. And if the nickel concentration is 0.04, and for every one of those you get two of those, then the chloride concentration should be 0.08. And that means we can just kind of bypass all that information and get to 0.08. So sometimes, yeah, I'm sorry to say, you're going to have a bunch of distractors to deal with on that one. Our next question deals with preparing solutions. And if you haven't seen my previous video on how to prepare solutions, maybe check that out first. There's a proper way to do it using a proper piece of glassware. A student wishes to prepare 2 liters of a 0.1 molar KiO3 solution, molecular weight 214. The proper procedure is to weigh out, and then we have some choices, and then add. Are we adding water? Are we filling it? Or, what are we doing? So first, let's find out how much we're doing. Whenever you make a solution, you almost have to sort of imagine the finished solution, what it's going to be and what it's going to look like. And so we have to then think, well, how much solute is actually going to go in here? So let's do some calculations. We want volume times molarity equals moles, so we can figure out how much is in there. The volume is 2 liters. The molarity is 0.100 moles per liter. And that gets me 0.200 moles of KiO3. Now, if I multiply that by the molar mass, which is 214 grams per 1 mole, that gets me a mass of 42.8 grams of KiO3. All right, and so that narrows down. We get rid of choice C. Are we 42.8, 42.8, 42.8? Are we adding 2 kilograms of water? Are we adding water until the final homogeneous solution has a volume of 2, or are we simply just adding 2 liters of water? Whenever you make a solution, you always want to measure out your solute, put it in some water, get it to dissolve because the volume is going to change a little bit, and it might do some weird things. And also, if you start with 2 liters of water and then add some, you're going to be over 2 liters. So that's not a good laboratory procedure. You want to dissolve it first and then add water till the final volume is reached that you want. All right, next pause the video a moment. Please take a moment. Which of the following is the best method for preparing 100 milliliters of 1.0 molar KCl? Take a moment, pause the video, and solve, and I'll see you back here in a couple seconds. Okay, so here's what we do. I calculated 7.46 grams of KCl. So if you did that, then that's great, and we have all 4 choices with that. And the next question is, are we going to use a graduated cylinder, an Erlenmeyer flask, volumetric flask? Always pick the volumetric if you want it to be accurate. So 100 milliliter volumetric flask, and we're not sure if it's going to be exactly 92.54 milliliters of water, but we're just going to fill to the 100 milliliter mark, however much that takes, and that should give you our final result. Okay, next question. If 200 milliliters of magnesium chloride is added to 400 milliliters of distilled water, what is the concentration of magnesium ions in the resulting solution? So this is a dilution question. And in order to save some time, I'm just going to show you the solution on this one so you can try one of your own. And whenever you dilute solutions, you're simply adding water to it. You're not changing the number of moles of the solute that's there, you're just adding water to what is already there. So what happens is the volume is going to go up, but the molarity is going to go down because it's becoming less concentrated. It's kind of like Boyle's law, but for solutions. They're inversely related to each other. So the formula for this is V1M1 equals moles, but since moles are constant, that's equal to the new V1, V2, and the new M2, or the new molarity. So here we go. We're going to plug in 200 milliliters, 0.60 moles per liter, equals a new volume of 600 milliliters because we added 400. And what's the new molarity, which is going to be 0.2 moles per liter magnesium. All right, pause the video time again. If you'd like, 50 milliliters of 1 molar NaOH is diluted with distilled water to a volume of 2 liters. What's the concentration of the resulting solution? Take a moment, pause the video, and see if you can get this one. Great, and if you were able to get choice A as our final answer, then great, good job. Another quick dilution question. I ended up with a new molarity of 0.025 on that. Okay, so let's take a look at the next. What is the molarity of iodide ions? Okay, so when you do molarity, you can put out the molarity as the molarity of the entire compound that's there. Or what if you're interested in just one ion? Maybe it's particular to the reaction that you're running, and you want to know the total concentration of that, in this case, iodine. So what do? Well, it's one extra quick step. And the way it goes, again, to save time, what's the molarity of iodine? So here's what I did. 34 grams of strontium iodide. they gave us the molar mass, which is really close to 10 times that. So I just kind of rounded 0.100 moles, and that's going to be in 1 liter. And that makes the concentration of strontium iodide 0.10 moles per liter of strontium iodide. But here's the thing, here's the extra step. When strontium iodide dissolves, it turns into strontium and 2 iodines. So for every 0.1 moles of this, you're going to get 0.1 moles of this because it's 1-to-1 ratio. One of those produces one of those. But since one of those produces 2 of those every single time, the actual concentration of iodine is going to be twice that of the strontium iodide. Okay? And so you just have to multiply it by how many ions are actually in a formula unit for that compound. And you'll get your answer that way, which in this case was 0.2. And for our last couple of questions, I chose a couple of slightly more challenging ones. And you might see this on one of your exams if you're taking a challenging course like AP Chem. When 70 milliliters of 3 molar sodium carbonate is added to 30 milliliters of 1 molar sodium bicarbonate, the resulting concentration of sodium is, and we have our choices there. So it gets a little complicated up in here, and you might be like, well, what the heck is going on? Because what happens when this is added to this? The volume changes and the concentration changes, and also this one has 2 sodiums in it, and that one only has 1 sodium in it. So, it's easy to just throw up our hands and, get out of town. So let me show you the solution for this one. Sorry for a couple of little scribbles. Nobody's perfect, right? And what I did was I figured out the concentration of sodium for each one. And I'm going to show you a little trick to kind of simplify things down. In the first one, 0.07 liters times 3 moles per liter gave me 0.21 moles of sodium carbonate. But then for every 1 sodium carbonate, there's 2 moles of sodium. That's where the 2 goes, right in there. And that gives me 0.42 moles of sodium. I'm just stopping at moles. I just want to get moles that's actually there. The other one, same idea, 0.03 times 1. And this one only has 1 mole of sodium for 1 mole of sodium bicarbonate. So it's 0.03 moles of sodium for the second solution. And then we're going to dump them together. Now, what happens when something dissolves and it becomes an ion floating around in solution? It becomes completely independent of its past history. It does not matter where they came from or which solution it came from. The only thing that matters for the molarity is the total moles of that ion divided by the total volume that it's now in. Save yourself a ton of time trying to figure out extra steps in there. Total moles divided by total volume, because that's what's there right now after we mixed them. 0.45 moles is the total. 0.1 liters is what it's in. And that's the 100 milliliters, 70 times 30. And that come out as 4.5 moles per liter of sodium in that solution. And I have one for you to try in case you're an intrepid chemist and ready to do a little challenge. Same idea. Do the same thing I did. Pause the video, see if you can solve it, and I'll see you back here in a couple seconds. And if you got this one, you can consider yourself well on your way to mastery of solution stoichiometry. I got a total concentration of 1 mole per liter. There were 0.4 moles of chloride in the first one, because every 2, this was actually a slightly simpler one, and 1 mole of chlorine for every KCl. I got 0.4 and 0.1 moles. Total moles is 0.5, regardless of where they came from. Now they exist in this current solution of 500 milliliters, and that worked out to be 1 mole per liter on that. All right, so I hope you enjoyed our little challenging journey into molarity calculations. I hope you found it helpful. If you have a question, please send it to me in the comments. In the meantime, happy studying and have a great day.